Hello. How are you doing, Internet? We are getting onwards to day 6. And oh boy, yesterday was a lot of fun. What a roller coaster. I wonder what's in store for today. Now, so I had to watch the recording back yesterday in full just to get a picture of all the crashes and issues that I was getting, to figure out what I need to do in order to not hamper my productivity as much. And I came up with 2 things. So, first one, well, my editor was running out of memory, so I could actually fit the whole document in memory because my editor is so huge. Well, not huge, but it takes up quite a bit of space, and I had calculated that I had about 8 kilobytes of memory free for the documents, but that wasn't clearly enough. So I did a fix to my editor program so that when I run out of memory, I remove the non-essential syntax, like the color highlighting for the code. That frees up like a couple of kilobytes at least of space in RAM, so I can fit bigger document. So hopefully that'll be just enough for the code. And then the second thing I noticed was the issue that I was flipping disks. So I had to do 2 disks and I was flipping disks. And of course, we're not gonna do that anymore because I got this. Yeah, that's right. I have a second disk drive. So this one is an identical disk drive to the first one, a 1541-2. Just like this one that I have. So this way, I can build a tower of disk drives. This is probably how it was used back in the day. Just stack them up. And I can daisy chain these, and they should work pretty well. So they'll get their own device ID numbers, and I can then have the editor on one disk, and then the puzzle inputs, and then the program code on another disk. So that's gonna be perfect. Now let's see. So to get this hooked up, I need a cable. So this will be daisy chained. So serial cable here, and then serial cable goes to the daisy chain port on the other drive. Oops, actually my C64 is on. Well, maybe it's already done now. And then a power cable. Oh, and then what I need to do. So let me turn this off for a second. What the heck is that? Jeez, that was the wrong kind of airplane flying low. So then what I need to do is set up the device ID for this other drive. I think that might do it. Cool, so let's give this a try. Actually, let me put this. Let me move this in here so we can take a peek. Oops. Like this. So there's the tower of disk drives. That looks pretty majestic. And then let's put on the other disk drive as well. And oh, wait, what's going on? It came up with a red power light. Huh. Is there some kind of error? Well, let's give it a try. Let's give it a try. So if I put in a disk in here, and then let's boot up. So now if I do load index from 8, so this bottom one should be the drive 8. Yeah, it's doing the drive light. So now if I do list, perfect. Okay, so I have my programs here. And if I do load index from drive 9, it should access here. Ooh, no, device not present error. Crap. Did I do the... let's see. Power these off for a second. Let me double check the cables. I didn't screw something up. Oh, the serial cable wasn't on fully. Okay. Maybe that was it. So let's see. Load index from device 9. Yeah. Now it's accessing. And then if I do list, this is the disk we did for yesterday. Cool, okay. So now I have drive 8 and drive 9. Perfect. Yeah, this is gonna be such an awesome setup. Let's put it like this. Oh my. One thing that I don't know is, so like these fast loaders have this, I think they call this like the wedge command. So you have like / and dollar and percent and whatever. But I don't know how to specify the drive number. So this is drive 8 and this is drive 9. So I don't know how to specify that one with those. So now if I do, I think if I do C++64, it's gonna use the last drive that I used in a manual command. So yeah, so now it's 8. But maybe that's not gonna matter, because I think I'm just going to load all the files from using the wedge commands from here, and then manually load from this one. So I'm gonna be fine. Cool. All right. So Command A. We get to the AOC. Yep. And there's the 10 stars we already have, and now number 6. All right, let's go. Day 6, wait for it. The ferry quickly brings you across Island. After asking around, you discover that there is indeed normally a large pile of sand somewhere near here. But you don't see anything besides lots of water and the small island where the ferry has docked. As you try to figure out what to do next, you notice a poster on a wall near the ferry dock. Boat races, open to the public. Grand prizes and all expenses paid trip to Desert Island. That must be where the sand comes from. Best of all, the boat races are starting in just a few minutes. You manage to sign up as a competitor in the boat races just in time. The organizer explains that it's not really a traditional race, Instead, you will get a fixed amount of time during which your boat has to travel as far as it can. And you win if your boat goes the farthest. Ooh, I sense a search problem coming up. As part of signing up, you get a sheet of paper, your puzzle input, that lists the time allowed for each race and also the best distance ever recorded in that race. To guarantee you win the grand prize, you need to make sure you go farther in each race than the current record holder. The organizer brings you over to the area where the boat races are held. The boats are much smaller than you expected. They're actually toy boats, each with a big button on top. Oh, hi Akarimon. Oh, nice, you're streaming AOC once again. Yeah, I am. So this is the second year that I did, and it turns out actually that I haven't been streaming much else the whole year. So I originally created this channel to play some C64 games, but then yeah, life happens and you do other things. But yeah, now going on AOC. Okay, so tow boats with a big button on top. Holding down the button charges the boat, and releasing the button allows the boat to move. Okay. Boats move faster if their button was held longer, but time spent holding the button counts against the total race time. You can only hold the button at the start of the race, and the boats don't move until the button is released. For example, this document describes 3 races. The first race lasts 7 milliseconds. Glad to see that you're back. Oh, thank you so much. Yeah, are you doing AOC as well? Okay, so the document describes 3 races. First lasts 7 milliseconds. Record distance is 9 millimeters. Second race lasts 15 milliseconds. Record distance in this race is 40 millimeters. Third race lasts 30 milliseconds. Record distance is 200 millimeters. Your toy boat has a starting speed of 0 millimeters per millisecond. For each whole second you spend... Okay, I'm just not gonna say milli again. Thing you spend at the beginning of the race, holding down the button, the boat's speed increases by 1 meter per second. So, because the first race lasts 7 seconds, you only have a few options. Oh, okay, with C#, cool. Yeah. Yeah, that's quite a productive language. First race lasts 7 seconds. You only have a few options. Don't hold the button at all. The boat won't move. It will have traveled 0 meters by the end of the race. Hold the button for 1 second at the start of the race. Then the boat will travel at 1 meter per second for 6 milliseconds, reaching a total distance traveled of 6 meters. 2 seconds. Keeping the boat speed 2 meters per second. Yep. Okay. Since the current record for this race is 9 meters, there are actually 4 different ways you could win. You could hold the button for 2 to 5 seconds at the start of the race. But in the second race you could hold the button for at least 4 seconds and at most 11 seconds and beat the record. Total of 8 different ways to win. In the third race, 11 to 9. To see how much margin of error you have, determine the number of ways you can beat the record in each race. In this example, if you multiply these values together, you get 288. Determine the number of ways you could beat the record in each race. What do you get if you multiply these numbers together? Okay, so I need a pen and paper. Pen and paper. Where am I gonna draw this? Maybe here. Maybe here. Now my stack has to move a little bit. Okay, so so I'm holding down the button for k seconds. And the total time for the race, t total race time. So I'm gonna move at k meters per second. So basically, if I choose to do k seconds, I'm gonna move k times t minus k meters. So I spent k seconds to charge up, and then I spent t minus k seconds. Yeah, I think this should be right. So that should be kt minus k squared meters. And here 0 smaller equal k smaller equal t. So if k is 0, we travel 0 meters. If k equals t, this is t squared minus t squared. So we also travel 0 meters. So this is a parabola that has zeros at 0 and t. So it's like this. And the maximum is at t over 2. Okay. So let's see, if I have time equals 7, t equals 7, and distance equals, and it's asking where the distance traveled is greater than some d, so in this case 9. So that's, if this is f of k, that means that we're asking like f of k is greater than some threshold distance d. So kt minus k squared minus d greater than 0. Or actually minus k squared plus kt minus d greater than 0. So this is k must be, well, k is in the range, or like if it's equal, that's minus t plus minus square root t squared minus 4d over minus 2. Is that right? minus t plus minus square root of t squared minus 4d over yeah, okay. So this is the range. So this is the values where this occurs. And I can cancel these out. Okay. So let's see some examples. Time equals 7. So this would be 7 plus minus square root of 49 minus distance equals 9, 36 over 2. 49, 36, so that's 13. So 7 plus minus square root of 13 over 2. 7 plus minus square root of 13. So that's between 3 and a 4. Well, let's say that's 3.5. So 7 plus minus 3.5 divided by 2, which is between 3.5 over 2 until 10.5 over 2. Which is like 1.75 until 5.25. Is that anywhere close to the right answer for the first example? Yeah, 2, 3, and 4, and 5, yes. Perfect, okay, so I think this should be a closed form solution. But the trick is that this closed form solution includes floating point, which I don't want to do. On a C64. The number of ways. You'll no longer need a Commodore for this. Simple calculator will do. Yeah, that's right. That's right. Well, maybe I could use a Commodore calculator. I think they started out with calculators before they did computers. So I have a closed form solution. How number of ways. So I cannot just subtract here I cannot just subtract this, like the top range from the bottom range, and then round that down to, or can I? No, I cannot, because it has to be first rounded and then yeah. So basically the range is like t minus square root of t squared minus 4d over 2, ceiling of that, and then up until t plus square root of t squared minus 4d over 2 and floor of that. That's the range. Actually, I am going to try out floating point numbers for this. I'm curious now to see, like, does it even support them? Oh, and it crashed. How would I do this without floating point? I don't feel like doing a linear enumeration of any of this. I want to calculate these values exact. Can I square? What happens if I square this? No, there's still gonna be that root. Yeah, let's see what happens with floats. Oh, but I don't have, yeah. No, but it's okay because I don't have the facilities to print float numbers. I implement my own printf. Oh, but I have my own libc and this is gonna rely on floating point. Yeah, I don't think I can do this. Let's say f plus equals oh, but I need to do let's do like oh. Yeah, okay. Okay, so so I don't have floating point arithmetic at all. I think this is doing the addition. So I think I need to somehow tabulate squares. Like I did kind of like coarse approximation here. Like if I know that square root would be between 4 and 5. But I would need to also know no, yeah, no, this divided by 2 doesn't really change anything. Yeah, because it's gonna just shrink. So if I have, yeah, now I know. Okay, so so here this square root is gonna be like there's gonna be like t minus an integer part plus some decimal part. So if I enumerate squares, I know what this integer part will be. Like if I do like a tabulation of like 4, 9, 16, 25, so forth. I can look inside here and figure out like what this integer part is gonna be. Basically like do an integer square root function. And then there's this unknown decimal part that I haven't calculated. But because I'm dividing by 2, there's no way that is gonna affect this. This result. Oh, but actually, no. I'm going very complex about this, because what I can do is I can afford, of course, to evaluate this manually. So I just round in the worst direction. So I do integer square root like upper bound for this, and then upper bound. So basically I'm going further to the left than this could be, and then I round up, and then I evaluate this function once at this point that I get, and then nudge it by 1. Are you thinking of using integer representation of mantis x? No, no. Like, if I did like an integer mantis exponent, that would be akin to sorry, similar to emulating floats, and I think that would be just. But yeah, so now I know what I do. I'm gonna do int square root ceiling of int value. So for int I equals 1, int square equals I times I. If square is greater than equal to value, return I. So this is my square root function. Let's see how this works. Okay, so actually now I want to save this, so save, yeah, now I'm saving to device 9, so it goes to the top disk, 2023.6a.cpp. So let's see what happens. Well, that didn't go right. Okay. Well, square root of everything. Like, I just wanted to loop. What did I do there? I just wanted to loop until 20. Did I have a typo there or something? What the heck? 2023.68.cpp. What? Int I equals 0, I smaller than 20. And this keeps printing... What? What on earth? Oh! Oh, I don't... Plus I. That would be useful. Yeah, it might be pretty hardcore to try to do soft float emulation on the spot. Okay, so now this... Oh, perfect. So this is good. So square root of square root of 0 is 1. Okay, maybe that part isn't that great, but it's fine. It's it's fine. It's a little bit... Well, maybe I'll correct that one. If so, it's not completely mathematically wrong. So square root of 0 is 0, square root of 1 is 1, square root of 2 is... So square root of 2 is 1.4, but I'm rounding up. So it's 2. Square root of 3 is also 2. Square root of 4 is 2 exact. Square root of 5 is more than 2, so I'm rounding up. So this is basically square root of a number rounded up to the next integer. Actually, that's a weird name. Let me do square up. So that's like square root rounded up. And then I need another function for... Actually, let's... So the thing here is that I might need to tabulate these at some point. Let me turn this to U16 because that's probably what I'm gonna need. U16 square root down value. Now I'm thinking, can I just yeah, square root down. No, but this now has to be greater than, right? Okay, what did I screw up there? Let me see. Okay, perfect. That was just rather late here. Have a good day. Hope we can... Hey, yeah! Have a good evening over there, Akariamon. Catch you later. Okay, so... So now I'm gonna print %u square root up and square root down. I square root up, square root down. Wait, what? Data argument not used. Oh! Oh, I had I here. Okay, now, okay. So here's my square root function. Square root of 0 is 0. That's precise. Square root of 1 is 1. Square root of 2 rounded up is 2, rounded down is 1. 3 again rounds. 4 is precise, 2 and 2. 5 rounds up to 3 or rounds down to 2. And then 9 is 3 and 3. Square root of 10 is rounded up 4, rounded down 3. And then it's precise at 16. Okay, so these, I think these functions are now correct. So now I have this nice utility square root implementations. That I can condense just the way I like to do in these puzzles. Here's the nice compact square roots. Perfect. Okay. So now I think I can solve this thing. Oh, but I forgot to even save the puzzle inputs. Okay, so now I need to go and save the puzzle inputs. Is that the input? Time distance. I guess that is. Yeah, okay. So I'll save this. Save to device 9. 2023.example6.txt. Okay, and let's see, shift I, device 9, 2023.input6.txt. Wait, what? There's only 4 of those. Okay. Perfect. Time and distance. So, file f equals f open 2023.example6.txt. And now I'm gonna add here 9 read, so that I'm gonna read from the other disk drive. fscanf file time colon. So I'm gonna parse that, and then u16 times. Well, there were only 4 of those, so this can be just u16 distances 4. While f scan f n equals 0, f percent u, yeah, 2 times n plus plus, or times n greater than 0 plus plus n. And then we skip distance and then do the same thing. And we get the distances. For int I equals 0, I smaller than n plus plus I. Int f t distance times I distance is I. Yeah, I'm not gonna need this one again. So let's save this. And yeah, so this is one of the bugs that I have in my editor. Like, you can see, like, you're not, like, the editor is not showing the status bar messages again. So I need to reset this. And then reopen this file. This is something that I really should find time to debug. Yes. 2023.6a. So I think now if I reopen it, yeah, now it got it. Okay, and there should be a semicolon. Format specifies type unsigned. Yep. Why doesn't that work? Let's try running. 7, 9, 15, 40, 30 to 200. Okay. So that works. Something isn't. Well, that's some signed unsigned thing. I don't know. Oh, I do need to upgrade these to U32s in the war one. So, but let's do U16 now. U16 low equals T. Oh. U16T equals times I. U16 distance equals distances I. So low equals T minus square root up. T times T minus 4 times. Actually, let's do U16 determinant equals t times t minus 4 times, or not determinant but discriminant, I think is the accurate term. Yeah, let's change that to discriminant. Divided by 2. That's gonna be a shift. And then u16 pi equals t plus square root down of the discriminant divided by 2. And now I need to fix up my rounding. So u16, calculate the distance from u16 so wait, what do I do? I do calculate time and yeah, the distance limit. Wait, I want to evaluate the function. Oh, that's because in my graph this is not t but this is k. Yeah, that's what was confusing me. So yeah. So k, now I understand where I was confused. So k and u16t. Return k times t minus no. Return k times t minus k. Well, this I don't think this necessarily needs to be its own function, but whatever. So this low and high, these are the k values that I choose to prime the button. So while low calculate low k is smaller than the distance required, plus low k, and while calculate low k time, high k time is greater than sorry, smaller than distance, so we come back. What? Oh, too many. Yeah, okay. Save. So now I've done the fix up for the lack of floating point, and t equals this, distance equals this. Winning k values are from this to this. Total number are these. Okay, so from low k to high k minus low k plus 1. U16. I think we needed to multiply all of those ranges together. So small multiplied by high k minus low k plus 1. Okay, let's say. So how does this go? Oh, and then of course print total value so let me write this down. So from T7 to 9, 7 to 9, we win by priming between 2 to 5 seconds, so 4 different values. From 15 to 40, we win by priming between 4 and 11, 8 seconds, 8 different values. And 30 to 200, we win by priming between 10 to 20, so that's 11. Total equals 352. Okay. Let me compare this against the example number. So let's go visit the website. So these numbers were, yeah. Okay. Oh, 288. So I did get something wrong. 4 times 8 times... I got 11 and this is supposed to be 9. Oh, that is interesting. I did some mistake. In the third race, you could hold the button for at least 11 milliseconds more than no more than 19 and still beat the record. A total of 9 ways, and I got 11 ways. Oh, interesting. Okay. So why doesn't value 10... Oh, is it about equal? Because I was calculating that I need to equal the record, and here you need to get strictly better result than the... let's see, so... the third was... time 30 and distance 200. So that is... If we... So in my example, I'm priming by 10. So that's 10 times 30 minus 10. So 10 times 20 equals 200. No, that's way off. No, it was 10. Not... Oh, it was 200. Okay, yeah. So, yeah, that's the problem. So... I need to actually beat, not just meet the value. 288. Okay, that's the right answer. Okay, so not 352, but 288. Okay, perfect. So now I'm gonna save, and let's run on the actual input. Oh no, actually not, because because this, now I need to fix this. So I have all these U16s here, but the thing is that this value, this is quadratic, and I think there were like 3. Well, let me just run this, because I don't think, like, I'm gonna overflow my 16-bit integer. So when I run this, 15296, 15296. Yeah, distance is like 2. Or did I overflow? Actually, maybe I didn't overflow. Because k times t minus k. So k is between... k fits in 8 bits. And t is maximum 99. So that also fits in 8 bits. Yeah, maybe that is the right answer. I'm gonna go and submit that. Let's go. Let's go and see what happens. $15 to 96. Not the right. You too low. Oh, but then I needed to multiply all of those. So individual evaluation. Oh, silly me. Okay, now this store crash. Yeah, of course, this individual evaluation of the function wouldn't overflow, but then I multiply all those results. Wait, actually, that's gonna even overflow a 32-bit number. Because those are 16-bit numbers. Like, each result is a 16-bit number. Potentially. So this needs to be 32-bit numbers. And oh, but this doesn't matter. Yeah, it could be even bigger than. Let's see. No, I think this would be it. 211904. Yeah, 211904. Okay. Let's give it another try. $211904. Okay. Okay, yeah. Okay, so what's gonna await us in part 2? So I really like this part 1 because it was solvable in a closed form on pen and paper. That was fun. And then also I really liked approximating square roots with this integer arithmetic because I don't have floats. Yeah. Is part 2 gonna kill me? Okay, well, here goes. Part 2. As the race is about to start, you realize the piece of paper with race times and record distance you got earlier actually just has very bad kerning. There's really only one race. Ignore the spaces between the numbers on each line. So the example from before, no, instead means this. Now you have to figure out how many ways there are to win the single race. In this example, okay. Oh, we're gonna nail this. Okay, so example 9 2023.example2.txt. Oh, not example 2. 9. Oh, no. Ah. Oh, what does it do now? Wait, I didn't give a file name. I wanted to cancel. Oh, I have a bug. Bug in canceling. Ah. So now I think it was writing this whole document description. But yeah, so I need to do this and then save 9 2023.example6.2.txt. Let's do example6b.txt. Oh, but I need to concatenate this thing. How do I do that? I need to concatenate. Oh, whatever. I'm just gonna take this value. So that's 567179999, and then distance 3341135. 13502430. That is a 64-bit integer. 3341135 13502430. Okay. Yeah. Actually, let me... I'm not gonna bother with this file, so let me write this other thing down as well. 71530 and then 94200. Okay, and yeah, this restore function isn't quite working out. Okay, so reboot. And now the HDMI capture isn't syncing. Reboot. Okay, now everything is perfect. C++64. Okay, open 9 2023.6a CPP. So immediately let's save Ctrl-Shift-S. Save to device 9. And let's save this over 6B. Okay, and now what I'm gonna do is U64 time equals 71530. U64 distance equals 94200. And I am not going to need any of this. T, B. Discriminant low, high. And I don't have a mechanism to print 64-bit integers. Oh no, wait, do I? Actually, do I? Let's see what happens. Time, distance, not like that. And I don't need that either. Oh, it actually compiles. I'm not quite sure if I if I remember, I have implemented 64-bit integer printing, but I'm gonna see that right too. No, I don't. Okay, so void print U64. Remainder equals x modulus 1000 million billion. Oh, well, I don't have... Okay, well, I need to be a little bit creative here. Or actually, let me do the... let me do the nice way. So this is gonna be the reverse number, but it's gonna be fine. I will be able to interpret that. Is that gonna work? While x remainder, get the smallest digit and print it. Yeah, okay. Okay, so print 64 ik minus low k plus 1. Oh, this is this is so ghetto stuff. It didn't print anything. Why didn't it print anything? What's going on? Oh. Oh, I forgot to make these. Okay. Oh, this is absolutely massive. I might have problems here. I might have issues here. Oh, I didn't print the... Oh, goddamn. Let's say... Okay, so... Low K... Print 64 low K. Print F... High up... High K... range. And now remember, these numbers are printed in reverse order. Oh. Yeah, so these numbers will need to be read from right to left. Okay. Let me save this. So. Yeah, I need to beef up the 64-bit number printing. So range 71503, low K 14, high K 71516. Okay, let me double check with what the calendar says. Seven 503, 14 to 7. Okay, so that's absolutely right. That's absolutely right. Oh, this restoring doesn't work. I wonder why that doesn't work. It would be so much faster if that one did work, but no, it doesn't. I might have trouble with my square root functions. We'll see pretty soon. 6p CPP. Is there a way to calculate square root quicker? But we'll see. So 567 17999 and 334113 513 502 430. Okay, so what is this gonna do? It was instantaneous, immediate. 4 3 3 6 4 4 7 2. Is that the correct solution? Is that the correct solution? That's the question. Let me double check. 4 3 3 6 4 4 7 2. Yeah, okay. Advent of code. Answer 4 3 3 6 4 4 7 2. And it absolutely was. Yeah. Okay. That was fun. Oh, that was pretty cool. Okay. Day 6 done. And it was 2 cold stars. Let's see the calendar. There we have the stars. We have 12 of them to be exact. Ooh, perfect. Okay. Now, that was quite something. Oh, this restores your question. Okay, so yeah, 64-bit printing improvements. That's on the table for me. To make printf work with this huge number. But I think this was everything. So this was 1 hour 20 minutes of solution time. Pretty nice puzzle. I really like how they did a closed, like a problem that has a closed form solution in general. That made it much more enjoyable to do a little bit of high school arithmetic there. Alright, internet. I hope you have a great Finnish Independence Day. And I will see you tomorrow for the next one. Take care. Bye.